Hi, NA Physics, it's Mr. Neff. Let's talk about standing waves in tubes. And before we do, why should you always feel sorry for a shopping cart? I'll tell you at the end of the video. Say I take this vinegar bottle. I don't know if you can see, but it's got a little bit in there. And I blow across the top of it. I'm able to make a pretty loud sound. What's going on there? I'm sure everybody's tried to do that, by the way. If you've never tried that, stop the video right now and go find a bottle and do the same thing. What I just did right there is as I blew across the top of the bottle, I created air that was not nice and constant. As much as I tried to, there were times where I was blowing a little bit harder and times where I wasn't blowing as hard. And so what I did is I made some turbulent air flow across the top of there. And that got some things vibrating inside. The wave you heard came like all waves. Its source was a vibration. And so what will happen is that column of air that's inside of there will start vibrating. And the note that you get will be dependent on how long the air column is. You can see this kid has a different length air columns, and so he's going to get different notes. Incidentally, you could also hit the bottle with something, and that would make the water vibrate. That's really not what we're talking about here, but it is also a vibration. So one way to look at this is as you blow across the top of there, the air in the neck, it has some mass, and so sometimes whenever the pressure is a little higher, that makes that air in the neck go head down. Sometimes when the air is a little bit lower up here, then that makes it vibrate back up. And so the air inside the bottle is acting spring-like. It has a pressure, and it can allow that air in the neck to vibrate up and down. Now I found this nice simulator from Germany. A fellow named Walter Fendt has put up tons of really cool simulators, and this is one of the ones that he made too. And so here's what you just had right there. So here's the column of air that was in my bottle, and this is the end that was down by the vinegar, and this is the end that was out at the top that had the air blowing across it. Now look at something. Because these molecules over here are against the bottom, they can't vibrate anywhere. Look at those. As you see vibration going on over here, but over here on the left, nothing. It's against a closed end, and so it can't really vibrate. The complete opposite of that is true over here. Since this is an open end, it's able to vibrate with a really great amplitude. Look at this last molecule right there. Just watch that thing. Look how far it goes. So there's the farthest that it goes. I'm just going to leave that mouse right there. And it's going to go all the way over. Look at the ridiculous amplitude that it has. You see, and it went all the way over to there. And so all that is to say that if you have the right frequency to give you a corresponding wavelength so that you get a node over here on this closed end and an antinode over here on this open end, then you're going to get resonance. Remember that resonance was getting large increases in amplitude because you had one of those special frequencies. Now, you could see that if I make this a higher frequency, and this was well programmed, and so you can see, let me scroll this just a bit, you can see that before I had a frequency of just about 86 hertz. And this is done so that when I push this higher, you see what happened? It made a frequency that was, well, was that double? Watch it. 86, 258. Double? No. Triple. And so it turns out if you had triple the frequency, then you get that same thing. You get that over here you have a node. Over here you have an antinode. But if you look, you'll also see that there is a node happening here too. Look at this molecule. It's going nowhere. And so you can kind of see what you have inside of there. You have a node, an antinode. Look at here. Look at this large amount of amplitude we see both sides. And then a node over here and an antinode out at the end. So if you have a special frequency so that the wavelength makes it such that you get a node at the closed end and an antinode at the other end, kind of regardless of what happens in between, you'll get resonance. And in this case, what it's going to mean is you're going to get a nice loud sound. Now, before we leave this simulator, what happens if you get both ends open? And so now with both ends open, you can see that the ends now are going to both be antinodes. And so this time, you need to have a special frequency not to get node and antinode, but with two open ends, you have to get antinode and antinode. And so we can have a fundamental frequency, a lowest possible one that will give you that. Look at the end here. This one's vibrating a lot. This one's vibrating a lot too. The ones in the middle are not making any progress really at all. And you can see that if you had the special frequency so that you got antinode, antinode, now you could get resonance from this open. So the two situations are similar. They're similar to each other, but not the same. And they're similar to a standing wave on a string, but not the same either. So remember when we were talking about strings, and the lowest note that would give you resonance we call the fundamental frequency. Well, it's the same thing here. Remember with a string, the lowest note that would give you resonance had a node and an antinode in between. These two ends had to be nodes because those ends were tied together and they weren't able to vibrate anywhere. But the middle of the string was able to vibrate. Well, whenever you see a column of air, if you see a closed end like this, you know that that has to be a node. And if you see an open end like this or this or this, you know that that has to be an antinode. So you can see that on the closed column, the fundamental frequency is going to be whenever you have a node at the closed end and an antinode at the other end. On an open column, you're going to have an antinode on both ends. Now, we don't cover this in our class, but it's also possible to have a closed tube, and that would be a node and a node at each end, just like a string was. I want you to think about something. How much of the wave is being shown in the left picture and how much is being shown in the right picture? A hint is they're not the same amount. There's an amount of a wave shown on the left. Think about that for a second. And there's an amount of a wave shown on the right. Think about that for a second. Pause the video and start it again whenever you have an answer. So on the left, I have from a node to an antinode, or I have from the equilibrium line to a crest, or from the equilibrium line to a trough. That is a fourth of a wave. And so I'm going to say that the length of the tube, L, is equal to 1/4 of that fundamental wavelength, wavelength 1. If I wanted to show you the whole thing, I'll do it and then I'll undo it. If I wanted to show you the whole thing, I'd have to draw the rest of the crest, and then I'd have to draw an entire trough. And so the wavelength starting from here to there would be really, really long, 4 times the length of the tube. Sometimes people make a mistake on this, and sometimes they think, wait a second, I've got half of a crest and I've got half of a trough, so I have half of a wave. No, remember, there's only a crest or a trough or a high pressure or a low pressure at once, not at the same time. And so this is a way to show that it fluctuates between high pressure and low pressure, but it's not going to be high pressure and low pressure at the same time. What about the open column? On the open column, how much wave do I see? Well, I go from a crest down to the equilibrium line and then over to a trough. So that is half of a crest and half of a trough. And so if I wanted to show you the rest of the wave, I just draw the rest of the trough and the rest of the crest. So the amount that I have pictured here is half of a wave. And so I'll say on an open, the fundamental wavelength is half of it is equal to the length of the tube. How about an example of each? Take a look at this. It says, assuming a speed of the sound in air is 343 meters per second and the length of the tube is 75 centimeters, what's the frequency of the lowest note played by this pipe? So this could be, now it would be a really long bottle if it was 75 centimeters tall, but it could be a piece of a tube, it could be a musical instrument. regardless, if you have it closed on the one side and open on the other side, what's the lowest note that you could get out of this? Well, let's see. We know that the wave speed is the wavelength times the frequency. And if you can remember back from strings, we would say that those two had to correspond with each other. I could make the wave speed fundamental frequency and fundamental wavelength, or I could make them wavelength 2, frequency 2, wavelength 3, frequency 3, and so forth, as long as they match each other. So now, the frequency of the lowest note played is that fundamental frequency, that F1, and so I'll say that F1 is the wave speed divided by the fundamental wavelength. Now, the wave speed is 343 meters a second, and the fundamental wavelength is 4 times as long as the tube is. And so I'm going to say this is 4 times the length of the tube, or aka 4 times 0.75 meters. Mental math will tell you that that denominator is 3, and so I'm going to do 343 divided by 3. I did that on my machine. 114 hertz is it. Now, what if everything else is the same? It's just that this is open over here. Well, if that's the case, now the fundamental frequency is still the wave speed divided by the fundamental wavelength, but the fundamental wavelength on this one is 2 times the length, because I see twice as much wave in this bottom picture than I saw in the top picture, and I wouldn't have to extend it nearly as far to show you the entire wave. So I'm going to make that 343 meters a second, and I'm going to divide that by 2L. That's 2 times 0.75 or 1.5, and you're not surprised whenever you're going to get twice as much, 228 hertz on that. So everything else is being the same, just having this one end open versus having this end closed, it makes a sound that's twice as high. So I have a few more things to say about all of this, and I'm going to finish those up on the second video. Please sure to watch that, and I'll also give the punchline to that joke.